Hello, everyone. My name is Benjamin. I'm a master's student at Polytechnique Montréal under Professor Monsef Shua, and like you said, I'm presenting a presentation, our research project for AI for interpretable fault detection and diagnosis in industrial systems. So our goal is to make diagnosis models more trustworthy and reliable by designing them such that you can understand the reasoning behind a model decision. So the industrial systems that I'm talking about are mainly process systems, so oil refineries, steel making plants, pulp and paper mills, cement factories. And what these systems have in common is that they're all can be considered inherently dangerous. So they use flammable and corrosive materials, they operate at high pressures, high temperatures, lots of mass moving around. And if problems occur in these kinds of systems, then they can have catastrophic consequences. So risk to safety, the environment, cost due to downtime and maintenance. And these problems are called faults. And so these are defined as process upsets in which they exceed the capability of the process controllers, which mainly deal with mostly small disturbances. And due to the complexity of these kinds of systems, they can be difficult to diagnose these kinds of problems and quickly resolve them. And therefore, these kinds of diagnostic tools to detect and diagnose these faults can help prevent emergency or disaster situations. So currently, the established methods for these fault detection and diagnosis methods are statistical methods such as PCA or PLS, but emerging with all the AI hype is deep neural networks. And how these work is that you have your sensor data, so these are in the form of time series, and then you can input them into your neural network model, which could be an LSTM, a CNN, a transformer, and then it outputs a system state, so from normal state to a given fault class. And so it performs both detection and diagnosis at the same time. The advantages of these methods is that it has high classification performance because it's able to model nonlinearities, but at the same time, they're considered black boxes. And where, for such a critical application where a wrong decision can lead to these kinds of severe consequences, we need a model that provides more reasoning in order to trust them. And so our proposed solution is to turn this kind of black box model into more of a glass box and understand the decision-making mechanism within the model itself. And so what we do is that we take domain knowledge and we embed it into the model architecture itself, so how the nodes are connected, and in that way we're able to understand what they mean. In chemical process systems, which is what we mostly work on, is that we take the knowledge of the fault itself and how it travels throughout the system. This is called the fault propagation path. Then we turn it into a directed graph and then input these directed graphs into the model themselves as separate graph convolutional layers. And these are special layers that are able to process graph structured data. And so the model learns the faults using these graphs and these sequences. The graph representations themselves are disentangled, and so they have interpretable representations in terms of the node activations. So like I said, we can interpret based on the node activations themselves and by comparing them with the other modules in the fault. For example, say our model detects fault 6. We can analyze the node activations within the fault 6 graph itself and to see if the corresponding nodes that are activated match the propagation path sequence. At the same time, we can see why it doesn't classify, say, another fault, so fault 7, and by looking at the activations, and we can see that the activations do not match the graph or the sequence of that propagation path. And therefore, we can see why the model chose this fault 6 instead of fault 7 and be able to trust the model decision. So in conclusion, fault detection and diagnosis systems, they're important for ensuring industrial process safety and production efficiency. We can use AI through neural networks to create a more accurate system. And in order to be able to adopt them into practice, inherent interpretability can be enhanced by making the architecture more understandable by embedding the task with this kind of domain-specific knowledge. Thank you.